So it's a bit difficult to tell a lot of augmented reality in just 20 minutes, but I will try. This is basically a very short version of the lecture that are going on in the Faculty of Computer and Information Science in Ljubljana. And the lecturer is basically my colleague from the institute, from the lab of Visual Cognitive Systems, Matej Krista. And I also work in Pulp and Paper Institute here in Ljubljana. So as I said, the main topic will be to convey the main idea, so what is happening under the hood of AR, of augmented reality, and we will do this by overviewing a very simple case of augmented reality with the fiduciary markers. And then, okay, time permitting, we will see also how to emulate some of the visual artifacts that basically otherwise capturing the visual information. So where to begin?
Alen, lahko uporabiš mikrofon, se tukaj
Yes, sorry. So where to begin this presentation? Maybe
bliže. Mogoče na online. Sorry. Ja.
One. So maybe it is wise to begin with spending a few words about like ordinary reality. So how do we perceive it? So here it is important to emphasize the difference between sensing the reality and perceiving the reality. So basically, our reality, our perception of reality, so how the reality we are actually aware of, it's basically the interpretation of our sensory stimuli. So what does this mean? And for this interpretation, we use a lot of experience, a lot of prior knowledge we accumulate during our life years. So what's going on during this interpretation? Okay, the best way to describe this with two examples. So the first one is from basically from the Gestalt psychology. So our minds make a series of geometric assumptions when they are dealing with the real images, and this can lead to some paradoxes like one that we see here. So basically here we perceive a white triangle over these black circles, but in reality, of course, we don't see the white triangle, we just perceive it. So this is, in a way, basically a trick of the mind. So we perceive something we don't see. This principle can come very handy when dealing with the occlusions in the real world. So, for example, because of this, we can perceive a bicycle behind a tree. But in this case, we see here the particles. So the second example concerns the perception of light. So what we see here is the chessboard with an object on it. And of course, we know how chessboards look like. And we know that, for example, field A is darker than the field B. But in reality, this is not the case. They're both of the same color. But for us, for our cognition, is more important to know that this is the chessboard than that these two fields are of the same intensity. So we can discard this information. And it makes perfect sense if you can agree with this. So why I'm showing this? Just to tell that some processes that are very similar to what's going on in augmented reality are already going on in our minds, in our everyday life. So it's a bit of biological augmented reality. So in this context, where to put augmented reality? Basically, it's just another layer between the reality itself and our senses. So it even emulates our perception, our visual system to a certain degree. So we have artificial sensors, we have artificial processing units that have visual content. And okay, so what is actually, how to define the augmented reality? It's basically a real-time view of the real world, augmented with some additional computer-generated information. So this information can be of various types, and its purpose can also be very diverse. on one end, the purpose can be a pure and simple entertainment. On the other hand, okay, we can also use this way to convey some very useful information about things that we cannot perceive with our naked eyes, ears, and so on. Now, here is important to note that this process should go on automatically and in real time. Otherwise, it's not considered augmented reality. For example, the special effects in movies are in general not considered augmented reality, even though augmented reality principle can be used for generating. The second thing that is worth emphasizing is that this additional content must contain a specific semantic context with the real environment. And we will see in the following what this actually means. So today we will deal with visual augmented reality. And this field goes back to the year 1990, where when Xerox and University of Toronto tried to implement some kind of mixed digital desktop, where basically we would be able to manipulate paper documents and projected electronic documents. So nowadays this idea seems a bit funny, but at the time it was quite a good idea. So what to say more about visual augmented reality? Basically the main problem is the camera localization. So how to establish a relation between the scene and the camera. And from this we can use either computer vision techniques, as we will see in the following, or some sensors, typically GPS, inertial sensors, and so on. Okay, so now quickly two examples of visual augmented reality. The first is like example of book enhanced with augmented reality. Hope this works. No. Okay. No, I think the sound. So we see that this animation basically somehow supplement the illustrations in the book. So this is a basic example of augmented reality used for pure entertainment. I hope you got the idea. So let's move on. And this is another example which is in its nature more practical, so a more practical use of augmented reality. So basically, it's for firefighter interventions. The idea is that basically firefighters can spot more easily the very hot objects which should be avoided. So these objects are highlighted, as you see here in the corner, with some red color. And we use, there is on this special camera, there is the infrared camera, and the information from this infrared camera is blended with the video of the ordinary camera. And of course, we can use this to display some other additional information, for example, about the positions of other members of the team or some other information you can see. And now to the main topic of our presentation. So an example of augmented reality with fiduciary markers. So what's a fiduciary marker? It's basically, I mean, the main idea is that we have stored in our memory, our computer, a reference model of the marker, which we are confident that to detect in the scene. So from this deformed figure of a planar marker which we detect in the scene, we are then able to estimate the position and orientation of the camera. And if you remember, this was like, this is the main problem in visual augmented reality. So here we see the main steps. First we must detect the marker, then from This we have to calculate the camera orientation, and from the orientation we construct the projection matrix, which we then use to project our 3D model into the video. So these markers can come in various types. This is one example of the marker. Very complex example. So this uses From's method for planar object detection. We can consider this reference model of the marker, and this is how this marker is being tracked in the video. It tells us the position and the rotation of the marker in its relation to the reference model. Another video about this. Maybe. So the drawback, even if it looks very fine, the drawback of this method is that it's very time consuming, so it uses a lot of processing power, but on the other hand, this is less and less constrained. Okay, and this is another example of very simple marker, and we will use this type of marker in the following of this presentation. So it's a binary marker, which is very easy to detect, and it's now, we can say, the most common type of marker. We can see many examples of this marker on YouTube and so on. It basically consists of two parts, so this outer frame, thick black frame, and of this inner pattern. So it is very important. You will see in the we will see later why that this pattern inside is asymmetric. So again, the main steps, the main phases of this procedure, and basically each phase is associated with one problem we must solve. So the first problem we must solve is how to detect the marker in the image. And since we have now a very simple marker, this procedure is quite simple. So we have the input image, which we convert to a grayscale image, and then we binarize the image with a certain threshold. Now here we know that the marker will be such, and basically now is the best time to know this. In this phase we are actually concerned only about the outer part of the marker, only about this this frame, and we disregard the internal pattern here, but we'll see later when this pattern comes handy. And even more precisely, we are concerned with the points, with the corners of this marker. So basically we are just trying to detect the corner points of this marker. So we can focus on the darker parts of the image. That's why this banalization makes perfect sense. And the next step is that from these darker regions, that we segment these darker regions in connected regions. So what does this mean? Okay, so here, marked with the labels from 1 to 47, we see all the connected regions of these darker parts of the image. So you really see they are, even though they are darker, they're here marked in white, you really see that they are connected. And one of these connected regions is, of course, the outer part of our marker. But we don't know yet which. So to restrict this list of candidates for our marker, basically we help ourselves with some assumptions we know about this marker. For example, we know that it's rectangular and it has 4 corners. And to detect corners in a binary image is quite an easy task in computer vision. So basically, with this knowledge and also with some size estimate, we are able to constrict this list of candidates to just a small list of just a few ones. So where are we now? Basically, we have a very short list of candidates for our marker, but we don't know which one is the right one yet. So for that, we need to already calculate the orientation of the camera. And so now, in this part, we'll see how to deal with these other two problems, so how to calculate the camera orientation and how to correctly project the object. So for this, we help ourselves with the pinhole camera geometry. What's a pinhole camera? It's basically the most rudimentary camera available. Basically, everyone can construct this kind of camera at home. But for us, it's more a mathematical model that describes the relationship between the coordinates of a 3D point and its projection onto the image plane. So basically, we use this mathematical model to simplify our problems so that we can deal with them in like linear terms. And now that we know about this model, we can also define the homography. So assuming a pinhole camera model, any two images of the same planar surface in space are related by a linear transformation, which is called homography. So here we have examples of two images. One is rotated in two dimensions, and okay, we can use homography to basically project any single points from this image to this image. So this is very similar to our problem. So the assumption, maybe I forgot to tell this, the assumption of our reference model of a marker is that it is basically located at the focal point orthogonal to the optical axis of our camera. So basically, if we're able to calculate the homography from the detected marker to our reference model, we also know from this homography the parameters, external parameters, so the orientation position of our camera towards the marker. So this is why homography is useful. So we basically, if we assume this is the marker, we have 4 corner points of the marker, and we have 4 detected points of marker candidate in our image. And then from this point, we must calculate the homography. Okay, try to make it quick. So how do we do this? We use direct linear transformation, which we don't have time to explain now. Let's just say that for each pair of points, we have 2 linear equations, which make a homogeneous system of equations. And from this, we can calculate the homography. So now with homography, we are able to rectify our candidate images into the coordinate system of our basically of our reference model. And now basically you can for each justification we have basically 4 possibilities, because we have 4 possible markings of the edges. And so basically we must make 4 homographies for each candidate. And then when we rectify in all 4 manners, we are able to match this against our reference model. And now you see why this requirement for asymmetric internal pattern is handy. So basically, you see now why it must be asymmetric. So this is the procedure for each candidate and for each possible rotation. We calculate the homography, we rectify the image using this homography, and then we match this. We compare the 2 patterns inside, and then we express the resemblance in like a value between 0 and 1. And of course, the orientation and the candidate with the highest resemblance is our marker. So this is how we were able to detect the marker and how we are able to detect the parameters, the basic orientation and position of our camera, which is basically the homography. From this, we can then calculate the projection. We won't go in depth in this procedure, and with the projections, we are able to basically project our points into the image. And this is the final result. So you see now that this procedure, we are basically able to respect the geometric context of the real environment. And this is the things that I was talking about in the introduction, about how this added context must respect some context restraint towards the real environment. Now here we have another example of an object which respects the geometric context, but somehow doesn't fit inside. And we can see why, because we have here an example of very poor image quality, while this object is very sharp, very crisp. So every photographer knows that, and camera knows that captured footage is subject to various artifacts, various optic artifacts that arise. And if we are able to emulate these artifacts on our content, the augmented reality we produce will appear much more authentic. So in a way, we even extend the meaning of like maintaining the semantic context with the real environment. Basically, we extend what is basically our environment. So instead, I mean, we must also then pay attention also to the lens, to the parameters of our camera, to the sensors, and even maybe in the end to some video compression artifacts. So, okay, let's see quickly two examples of these artifacts. The first is chromatic aberration, which is caused by the fact that different light wavelengths refract at different angles when they pass through the lenses, and the effect of this is that the image gets blurrier when we approach the edge of the image. Then, the second example of such an artifact, basically it's like some geometric distortions, which is caused by lens imperfections. And again, this effect is more pronounced as we approach the edge of the image. And now, really the last thing, so an example of how these artifacts can be applied to our edit context to make it more real. So here we have a very blurry image of a camera that is obviously in motion. And we try to put this additional content inside, so this subpart character. So, and now we will see step by step how this happens. So the first step is to apply the lens distortion. Then we do some sub-sampling of these graphics. And we mix also some colors. Then we apply some Gaussian filters, some Gaussian blurring. And in very similar fashion, with some blurring, we've also emulated the motion of the camera. And then the final step is to make another subsample which basically emulates the Bayer sampling. So basically it emulates the Bayer mask, which is how the sensor in every camera looks. And we also add some image noise. And this is then the final result. So as you can see, this image is very well blended into the environment. And here you can see the difference if we don't do this. So it's quite some difference. So now this concludes this presentation. I hope you had fun. Thank you very much.